Hello, everyone, and welcome back. In this lecture, we're going to continue our discussion of sequences, and in particular, we're going to focus on convergence sequences. Now, the goal of this lecture is to understand how we can take, say, two convergence sequences and put them together to form other convergence sequences. So, for example, if I add two convergence sequences, then the limit we would expect of this addition of convergence sequences to be the addition of their limits. Same thing if I want to multiply these things term-wise. So that's going to be the goal of this lecture. We're going to prove one large theorem that tells us how we can combine and provide algebraic combinations of convergent sequences to produce new convergent sequences. So let me start by showing you the main result that we're going to prove today. And we're going to first provide a few auxiliary results before we can get into the proof of this result. So here's the goal. We want to prove this theorem. So we're going to say, suppose xn and yn both converge with xn going to L and yn going to M. This is as n goes to infinity, of course. Then we have the following. The first one is that xn plus yn converges to L plus M. And similarly, if we subtract these things, this goes to L minus M. Also, if we multiply them term-wise, this goes to L times M. And the last one gives us division. It says xn divided by yn converges to L divided by M, provided we can actually do this division. So M doesn't equal to 0 and yn doesn't equal to 0 for all n and n. All right, so there's a slight stipulation on this one here because we're doing division. So like I said, the goal for the lecture today is to prove this. These are algebraic combinations of sequences. But in order to do that, we're going to provide some little auxiliary results. So these are referred to as lemmas. They're little stepping stone results that build us up to the big theorems. These are the main results. So first thing I want to do is I want to introduce a definition. So a sequence that converges to 0 is called a null sequence. Null sequence. Okay, so if your sequence converges to 0, it's called a null sequence. So an example of this would be 1 over n, right? That converges to 0. Now, we're going to have a small little lemma here, and it says that the sequence xn converges to L in R, so it has some limit, if and only if xn minus L converges to 0. Okay, so your sequence converges to a limit L is the same as saying that if you take L off of every element of the sequence, then this thing converges to 0. Equivalently, this is saying that xn minus L is a null sequence. Now, this may look maybe a little bit intimidating. I'm not 100% sure, but once you see the proof, you'll realize that this is actually just extremely straightforward. So this is telling us, let's take a look at this. So by definition, xn approaches L if and only if for all epsilon greater than 0, so we're going to use the definition, there exists a natural number n, so this again corresponding to epsilon, So I'm just writing down the definition such that when you look beyond this capital N in the sequence, this gives you that xn minus L in absolute value is less than epsilon. So, but this is also equivalent. So it's just a way of sort of rearranging these things and how you look at them to prove this lemma. It's nothing really more than that. So this is equivalent to saying, sorry, the absolute value of xn minus L minus 0 is less than epsilon. But take a look at this. The first piece, xn minus L is less than epsilon. That's xn is converging to L. That's the definition. Whereas this piece right here that I just wrote, this is xn minus L is converging to 0 as n goes to infinity, right? It's all, again, all it is just writing it out, right? It's just where I put the brackets and what I put the limit to be. So this is, which is equivalent to the statement. So just what I have in blue here, that xn minus L converges to 0, since, well, clearly these things are equal to each other. Boom. Nothing needs to really be done here, right? It's once you actually start writing it down, you realize that this is quite trivial. Okay, so that's one little piece. Okay, it says if I have a sequence converging to a limit, then if I subtract the limit from every single element in the sequence, this thing is actually going to now converge to 0. It'll be a null sequence. All right, let's propose one more small lemma. And this one says that if you have a null sequence, so if Sn converges to 0, and if Tn is bounded, doesn't have to converge, could be -1 to the n plus 1 if you wanted, then Sn times Tn goes to 0. So what does this say? It says if you have a null sequence and a sequence that's bounded, then if you multiply them together, the null sequence is going to sync this thing and produce another null sequence. So again, the proof of this is quite simple. So first of all, since Tn is bounded, there exists some positive capital M such that Tn is less than or equal to M for all n greater than or equal to 1. All right, that's just the definition of being bounded, right? It has an upper bound and a lower bound. We use the absolute value here to account for both of them, right? You can always open this thing up, and this is minus m is less than or equal to Tn, which is less than or equal to m, telling you you have a lower bound of minus m and an upper bound of capital M. Okay. So then let's let epsilon be greater than 0. So of course, we want to show that this thing converges. We need to choose an arbitrary positive number epsilon. And we can say since Sn converges to 0 as n goes to infinity, right? We know that Sn converges. Well, then by definition, there exists a natural number such that if I look beyond that natural number, capital N, this implies Sn minus its limit 0, which of course is just the absolute value of Sn. This thing is less than epsilon over m. Again, epsilon over m, this is a positive number. So of course I can make Sn smaller than this. This is just the definition of converging to a limit for a sequence. So now, if I take n greater than or equal to capital N, this implies, well, if I take Sn times Tn minus 0, so I want to show that this is smaller than epsilon to show that this is a null sequence. Of course, this is just Sn times Tn, which is just in absolute value. You can open these things up and say it's the product of the absolute values, which Sn is less than epsilon over m. Tn is less than m. And so now you can see that these m's are going to cancel. I was very clever about where I'm putting them here. That's why I said I want Sn less than epsilon over m, because now I've got Sn times Tn minus 0 is less than epsilon in absolute value. So therefore, Sn Tn converges to 0 as n goes to infinity from the definition. And by that, I mean from the definition of convergence. So that gives me what I wanted. So that's nice, right? This is a really, really nice thing here, but it may not be exactly clear why we put these in, right? Again, remember, the whole point of this video today is to show that this massive theorem is true. So then I said I'm going to have to introduce some little stepping stones to get there. So I have this first lemma, the sequence xn converges to L if and only if xn minus L converges to 0. So I sort of pose this, I turn things into a null sequence. And then my next one says that if I take the product of a null sequence and a bounded sequence, then I get another null sequence. Okay. So again, it's not immediately clear how these are going to help us, but they are little stepping stones so that when I return to the proof of the theorem, remember where we started, what we cared about today, I'm going to be able to use these things. So I'm going to be able to plug them in as necessary to greatly simplify my work. And if you've ever read an academic math paper, you'll see that this is how they're typically organized. They give you the main result up at the top, the huge theorem that is going to be the main result of the paper. Maybe there's 1 or 2 or 3 of them. And then the paper is typically broken down into little auxiliary lemmas that don't quite, you can't really see how the whole thing fits together until the very end where you do the theorem and you say, okay, first I need this. Well, that follows from my first lemma. Next, I need this. Then that follows from my next lemma. And so now you've really, really decreased the size of that proof for your main result. You've broken it into a little bite-sized pieces. Okay, let's see. Let's do the proof of 1. So if we turn back here, this says that xn plus yn converges to L plus m. We're going to use the fact that xn and yn are individually convergent sequences. So as always, we need to prove something's convergent, start with epsilon positive. Then there exists an n1 greater than or equal to, in the natural numbers, such that if you take n beyond n1, this implies that xn minus L is less than epsilon over 2. Now, when you see me doing epsilon over 2 or epsilon over 3 or something like that, you should immediately think triangle inequality is going to come in here. And I'll show you exactly where. But let's proceed with this. And similarly for yn sequence, you can find an n2 such that if n is beyond n2, this implies yn minus m is less than epsilon over 2. So now let capital N equal to the maximum of n1 and n2. So you saw this trick done in the previous lecture as well. You know that everything works well for the xn sequence beyond some number, and you know that everything works well for the yn sequence beyond another number. Well, then just look beyond both of them to make everything work well for both of them. So that's where we're going to take this capital N to be the max of n1 and n2. Then if n is beyond capital N, well, then it's beyond n1 and it's also beyond n2. So this implies, remember, we want to show that xn plus yn minus L plus m is less than epsilon. What I can do is I can first rearrange here. So this becomes xn minus L, and this becomes yn minus m. Then we hit this with a triangle inequality. So we distribute the inequality or the absolute value over the elements of the sum. Right, so maybe it's nice to put a little note here so we know what happened. triangle inequality. I told you it was coming. You will be able to anticipate when it's coming when you see epsilon over 2s. I can guarantee you that. If you get nothing else out of these, that will be the thing that sticks with you. And here we get that xn minus L is less than epsilon over 2 when n is greater than or equal to n1. Similarly, yn minus m is less than epsilon over 2 when n is greater than or equal to n2. So this is when n is greater than or equal to n2. This is when n is greater than or equal to n1. Since we're beyond both of them, that holds, and this gives me epsilon. So therefore, xn plus yn converges to L plus m. Okay, so then the next one is dealing with subtraction, but this is basically the same as the previous case. So I'm actually going to leave this one out. So to show xn minus yn converges to L minus m, just follow as in part 1. So I'm going to omit that piece of the proof. Again, if you want to challenge yourself, if you're working along at home, try that out. Try and prove it. It should be nearly identical. It's just one application of the triangle inequality. Okay, let's do one that's a little more fun. Okay, we're going to show that xn times yn converges to L times m. First of all, since yn is convergent, go all the way back to the second lecture. We know that this means yn is bounded. Right? We proved that. We said that if yn is convergent, then it's Cauchy. If it's Cauchy, then it's convergent. And we had that string of it, or that transitivity that told us if it's convergent, then it must be bounded as well. So look at how nice this is going to wind up being. If I take xn yn minus L times m, I want to show that this thing is a null sequence based on my first lemma. Well, here's what we'll do. Maybe I'll color code these so you can see what I'm doing. I'm going to add and subtract the same term into this. Okay, so I put it in green just to highlight to you what I've done. But I've added and subtracted the same thing. So it's 0, right? Imagine going forward 5 years and then backwards 5 years. Well, you're right back where you started. So the advantage that this has, though, is that now I can factor. And so here I get L times yn minus m. And let's take a look at this. Okay, so maybe let's put some comments in blue. This is a null sequence. This is a null sequence. And maybe we'll put the other piece in red. This is bounded because it's convergent. And similarly, this, just the constant sequence L is of course bounded, right? Because it doesn't go anywhere from L. So that tells me that the first piece converges to 0 and the second piece converges to 0. And again, let's put a little note why that's true. This is by second lemma today. So clearly this limit is equal to 0. And what this shows you, right, I didn't even have to use any epsilons here. I just used all of the logic that I built up from the lemmas. But this tells me that xn yn minus lm is a null sequence, which from the first lemma today, implies xn yn goes to L times m. That's how little auxiliary lemmas work, right? We can see that the load has been significantly lightened on us because all I really need to do is a little bit of algebraic manipulation, not even that much, right? The only thing I actually had to do was add and subtract those green pieces right there. That's it. After that, I just looked at it and I said, okay, well, null sequence times something bounded. My second lemma told me that goes to 0. Second piece is also a null sequence times something bounded. Again, second lemma tells me that goes to 0. And so I found another null sequence, and therefore, now I can just use my first lemma from the day. Okay, let's do the last one here now. We're going to do the division of these. Okay, so from 3. So from the third part today, if 1 over yn converges to 1 over m, we would have xn over yn converges to L over m. Right? So if I can define a new sequence, maybe call it Zn, which is 1 over yn, then if Zn converges to 1 over m, it's again a convergent sequence. And so I can multiply it by xn. And from part 3, where I said if you multiply convergent sequences, the limit is just multiplying the limits, I would have the result. Hence, we will show 1 over yn converges to 1 over m. That's really all that we need to do. So first, let's note that if you take 1 over yn minus 1 over m, find a common denominator here. So you multiply the denominators, you're going to get yn times m on the bottom. And on the top, you'll get yn minus m. Now, order doesn't matter. You might have written m times yn, but it's in absolute value. So order won't matter here. But this becomes yn minus m times 1 over yn times m. Now again, let's put something in here. This is a null sequence. So if we want to show that this thing is going to 0, so let's write this out. Since yn minus m is going to 0, it now suffices. So it suffices to show 1 over yn times m is bounded. Maybe pause the video and ask yourself, why is that the case? And the reason for that is from the second lemma today. Again, null sequence times something bounded tells you that your that product goes to 0, which would therefore tell you that 1 over yn minus 1 over m goes to 0. And so you can use the same chain of reasoning that we used in the previous exercise or the previous part to show exactly what we need here. Okay, so now there exists a capital N such that n greater than or equal to n implies that yn minus m is less than the absolute value of m over 2, right? So a capital M could be positive or negative. So we want to make sure that this thing is positive here because this is an absolute value. Again, the lemma is assuming m does not equal to 0. So this is in fact a positive number. But if I open this up a little bit, I am going to get the absolute value of m over 2 negative is less than yn minus m, which is less than the absolute value of m over 2, which gives me, so if I rearrange this thing, I get m minus the absolute value of m over 2, which is less than yn, which is less than m plus the absolute value of m over 2. And all I care about is that bottom limit there. So you can work out some cases if you'd like on the side, but this shows me that the absolute value of yn is bigger than m over 2. And this is again for all n greater than or equal to n. Okay. So now what do we have? Now we can say this implies that 1 over yn times m is less than 2 over the absolute value of m squared, right? Because yn is bigger than absolute value of m over 2. Flip everything, and you get 1 over yn is less than 2 over the absolute value of m. So thus, 1 over, sorry, maybe we should point out this is for every n. So this is for all n greater than or equal to capital N. So this is just like what we did a few lectures ago. We've bounded infinitely many of the terms. We only have finitely many left. So this tells us thus 1 over the absolute value of yn times m is bounded by, so again, we have infinitely many terms bounded. So we just need to look at something that bounds the first few terms. So you can take the max of the first capital N terms. Again, we did this similarly in the lectures. 1 over yn minus 1 times m. And then finally, 2 over the absolute value of m squared. I apologize for having to squeeze that in there, but there are only finitely many terms here. So max exists because b/c only finitely many terms. Again, think of my analogy. There's 10 of us or something like that in the room, then somebody's got to be the oldest, right? There has to be an actual maximum. But that shows that it's bounded, and now all the dominoes fall, right? Because that's bounded, that tells us that 1 over yn minus 1 over m is a null sequence, which tells us 1 over yn converges to 1 over m, and therefore xn over yn converges to L over m, right? So we have this big chain of results that would have taken a lot of work had we not proven those simple little lemmas. Okay, let's close it out with some little simple examples. But we can see here, for example, 1 over n squared. Well, this thing is equal to 1 over n times 1 over n, and this is going to converge to 0 times 0, which is equal to 0. And more generally, 1 over n to the power of, say, k converges to 0 for all k natural numbers. All right, so now I don't need to use the Archimedean property anymore. Life is good, right? I have these really, really simple little properties. Similarly, maybe if I do xn is equal to 1 minus 1 over n, well, the constant sequence 1 just converges to 1, right? We already proved constant sequences converge to their constant value. So this thing converges to 1 minus 0, which is equal to 1. And maybe I should be indicating that this is by part 2, and this one was by part 3. But you can have all kinds of fun with this, and you can continue to, I can give you big complicated sequences, and you can tell me, what things converge to, if they do converge. Similarly, we can use the limit here, and we could say xn equal to minus 1 to the n plus 1 over n. So it's alternating here. Well, this is the sequence minus 1 to the n plus 1 times the sequence 1 over n. And here again, this is a null sequence. The minus 1 to the n plus 1 is bounded. And so this thing converges to 0. It tells us that, again, we have a null sequence, and this is by our second lemma. So we have now a really, really nice way of finding limits without doing a whole lot of work, right? We don't have to do the epsilons anymore. And we can use the relatively few that we've actually proven, right? We've proven 1 over n converges, we've proven constant sequences converges, and we proved like r to the n where R is between -1 and 1 converges, right? Those geometric sequences. But now we can sort of combine these things and mix and match them in all kinds of ways that might follow this theorem. And we can make big, long, complicated expressions and figure out where they converge to. Okay, so this significantly lightens our load, right? It makes things a lot easier to work with, and it helps us not have to say, let epsilon be greater than 0 and do all of this work and cascade all of our issues. This allows us to just sit down and do some old school algebra and just say, xn converges to L, yn converges to M. Therefore, if I add these two sequences together, then I just get the sum of their limits when I take the limit here. So this is just a massive ease on a lot of our work going forward.